Right. Good afternoon, everyone. So, welcome to the lecture of the elementary principles of the chemical processes. Right. As usual, let's have a quick recap about what we have learned last week. Last week we talked about the pressure, volume, and temperature relations with the gas mixtures. So, especially we want to know how to use case rule to find out the pressure, volume, or temperature. So, assume we have three types of the gas in the chamber, in the system. Let's say A, B, C. So, because this system follow non-ideal, the system is a non-ideal system. So we want to use case rule to find out the pressure, volume, and temperature relationship. So assume we have a gas mixture 1, 2, 3, and then we need to find out the critical pressure and the critical temperature of the species 1, 2, and 3. So you can get the information from a table. So I will give the table to you in your final exam. Okay? And then once you find out the critical temperature and critical pressure for species A, B, C, then you need to, and next you need to know the fraction. The fraction A and fraction B and fraction C in the system. And then after that, you need to know if these three type of species contain small molecules like hydrogen or helium, you need to use Newton correction to have 8 units of the pressure and temperature into this critical temperature and critical pressure. So, and after that, if you know the fraction and you know the critical temperature and pressure, and then you know the Newton correction, you can get what we call pseudo-critical constant. Okay, pseudo-critical constant, pseudo-critical temperature, and pseudo-critical pressure is represent the systems here. Okay. So once you know the pseudo-critical constants, and you need to find out if you have temperature and pseudo-critical temperature, pressure, and pseudo-critical pressure, then you can get the information of the, we call pseudo-reduced constants, like pseudo-reduced temperature, pseudo-reduced pressure, or pseudo-reduced volume. So you can find out 2 out of these 3. Okay, using these 2 information. Right, so once you have pseudo-reduced constant, and you go to compressibility chart, because generalized compressibility chart, this one. Okay, because this is pseudo-reduced pressure, pseudo-reduced temperature, and pseudo-reduced volume. 2 out of these 3 information, you can get a compressibility factor. So this is what we call ZM. M stands for mixture. Okay, so once you have mixture, and then you go back to compressibility factor equation of state. So you have P over K equal to ZM RT. So you have ZM, and if you have a pressure and temperature, you can get volume. If you have a volume and temperature, you can get pressure. So you can get if you have you can get 1 out of these 3. Okay. So this is the summary of the 5.C, a gas mixture using a compressibility factor, or we call case rule. Right. So let me summarize the chapter 5. The chapter 5 we talk about single phase. So for the single phase, you have solid, liquid, and gas phase. For the solid and the liquid, it's very easy. So you just know how to measure the density of the solid and liquid. But for gas, you need to know that you need to know the system is ideal gas system or non-ideal gas system, and you can also realize this is a single gas or multi-components. Multi-component means that you have a gas mixtures, okay, like helium, argon, carbon dioxide, for example. So let me use this table today. You know that for a single gas, if you use ideal equation of state, this is ideal system. Ideal gas system, you use PV equal to nRT. This is easy, right? However, for the multi-components, you also this system also obey ideal equation of state, which is PV equal to nRT. But you need to realize the partial pressure of A species times V volume equal to the moles of A species times RT. And this is what we call Dalton's law. Dalton's law, right? Dalton's law. And Amagat's law is that the total pressure times the volume of A in the system equal to the mole of the A species times gas constant times time. So this is called what we call Amagat's law. Right, for ideal gas, for the single gas, for the single gas in a non-ideal gas system, the first one we learn is variable equation of state. Remember, variable equation of state. And if you remove the term C, term D, term E, now that's what we call truncated variable equation of state. Right? And after that, we learn cubic equation of state. There are two examples we learn here. One is that van der Waals equation of state, and the second one is SRK equation of state. Okay, and the third one is called compressibility factor equation of state. Okay, so what we learn is Z. Remember Z here. Okay. For the multi-component non-ideal equation of state, we use case rule, the one I just showed you, right? Okay, this is the summary of the chapter 5 for the gases. Okay, the mixture rule we don't introduce you here because it is more complicated, but it's more accurate. Right, so gas is a kind of very important, this is called fire piston. The fire piston is that we use is a non-ideal gas system because this is a fire piston, sometimes called a fire cylinder or a slam rod fire starter. So you can make the fire using a very simple principle of the relationship between the pressure, volume, and the temperature. So it's a device of an ascent origin which is used to kindle fire. Okay, it used the principles of the heating of the gas. Okay, in this case it's air. Okay, by a rapid and adiabatic compression. Adiabatic, what does that mean? Adiabatic. 绝热. Okay, 绝热. Okay, to ignite a piece of the tinder. Okay, which is then used to set light to the kindling. Okay, so you can have a fire in this cylinder, or syringe. Okay, the plunger allows you to compress the air very quickly. The sudden but extreme increase the pressure will cause the temperature of the air inside to rise equally, suddenly, and extremely. So you push this piston to this cylinder, and very fast. So the pressure will increase very quick. If the pressure increases very quick, that means molecules will collide very quickly, and the fraction will increase. So you will increase the temperature very fast. So if you increase the pressure and thereby the temperature increase, it can go up to 200 more than 200 Celsius. So you can ignite the fire if you have a small tinder inside. So I want to show you some. Right, okay. So now let's move to chapter 6. Chapter 6 is the multi-phase systems. So in chapter 5, we only talk about one phase. It can be gas, liquid, or solid. But now we are going to move to a little bit complicated system called multi-phase systems. It can be gas, liquid, or gas, solid, or liquid, solid. So when you see a glass of water here with ice cubes inside a glass of water, this is a multi-phase system, right? You have water and you have ice cube. Okay, so this is a multi-phase system. So when you want to change the phase, this is called phase change operations. So you want to change the phase from solid to liquid. How do you call this? Liquid, when you want to change the liquid to solid, for example, you want to change liquid to solid, what does that mean? How do you call this in English? Freezing, right? Freezing. You freeze. Think of ice, water, and vapor, water vapor. So liquid to solid, we call freezing. How about solid to liquid? Solid to liquid, we call melting, right? We melt. Solid was melted. Okay? So solid to liquid, melting. How about liquid to gas? Liquid to gas. So this water and gas was vaporized, as liquid was vaporized, right? So what we call evaporation. Evaporation. How about gas to liquid? Gas to liquid is called what? Condensation. Condensed. Gas was condensed to become liquid. Okay, we call condensation. So these are the operations. How about gas, solid to gas? Solid to gas. Solid to gas. Sublimation. Sublimation. 升华, right? How about gas to solid? Gas to solid, what does that mean? How do you use English to describe this? Deposition. Deposition. So these are the operation. These are the phase change operation. You can change liquid from liquid to solid, solid to liquid. So you can do it in the laboratory, but you can do it in the industry, right? So you are the chemical engineering student. So we want to do it large scale. So you want to think how to do it, how to design a process to make this happen, to make liquid become solid, to make solid become liquid. So this is separation purification process of A and B species by phase change operation. So not only you can do this in single phase, single species, but you can do it in a mixture like A, B, C. So this is what we call separation. So for example, remain A in the original phase and most of the B transfer into a second phase. Okay. So for example, you have a mixture of the water and acetone. So you want to separate these two, right? So water and acetone, they are mixable, okay? And then they are mixture. So you want to separate these two. You use what? Evaporation, right? Or we call distillation. The process is called distillation, 蒸馏, right? Okay, how about nitrogen, oxygen? How do you separate the gas? You know that in the air, what you want is air, what you want is oxygen. You don't want nitrogen. Well, but in the food industry, you want nitrogen. You don't want oxygen. Why? Because oxygen will oxidize the food, so the food will get rotten easily. So you want to have the process. You want to introduce nitrogen in the industry, so you can keep the food longer. right? So how do you separate nitrogen and oxygen? You want oxygen or you want nitrogen. So this is kind of industrial process. Okay, I'm going to show you this later. So, but before that, this is phase transition. As I just showed you that from this gas, this is liquid, and this is solid. This is the phase diagram. Remember, this is the phase diagram. So from this liquid to gas is called vaporization, or we call evaporation. Both ways, okay. From the gas to liquid is condensation. Okay. So this is melting, freezing, sublimation, and deposition. Okay. Right. So the first one I want to introduce you for the separation and purification process is called leaching. What does that mean, leaching? You drink coffee. Do you drink coffee? If you drink coffee, you know that the liquid coffee is from a coffee bean. So you need to get something from the coffee bean and become liquid. So this is what we call leach. Leach is the one you transfer the things from the solid phase to become liquid, to be the liquid phase. I hope you, for example, this is powder. This is the powder of the coffee bean, right? And you pour the hot water into this pot, so you can get coffee. Okay. So the operation of dissolving a component of the solid phase in a liquid solvent, this is called leaching. Leaching. So in your final exam, if I ask you, please define the leaching or leach, and you can tell me, oh, this is from solid phase to liquid phase. If I ask you to give me an example, I'm sure you can give me the example, right? So hot water and the solid ground coffee beans, you can get a cup of coffee. Right. The second term I want to introduce you is called scrubber. Scrubbing. What is scrubbing? Scrubbing is a kind of absorption process, which is we want to get things from the solid phase to become liquid phase. And this is called absorption. Absorption is a process, absorption, a process in which a gas mixture contacts a liquid solvent and a component or components of the gases dissolve in the liquid. So you have something in the gas phase, and you don't want this in the gas phase. You want to remove this in the gas phase. So you use absorption process. And this machine is called scrubbing, or this process is called scrubbing. The machine is called scrubber. Okay? So this is scrubber. So for example, you have A, B, C, D components in the gas phase, and you introduce gas into this from here and go into this reactor. Oh, sorry, this is not reactor. Go into this scrubber. S-C-R-I-B-B-E-R, scrubber. Okay, and then you have water here. So you have a nozzle, and you spray water, and to have a wide area of the contact with the gas. So the water, the things which you don't want in the gas phase will be absorbed in the water, and then water eventually will be here. So you will have a water with the things absorbed. Okay? So this is called scrubbing, absorption column designed to remove undesirable components from a gas stream. So here I'll give you an example. When you burn a coal, the coal is from mountain. So a coal has a carbon, oxygen, hydrogen. Sometimes you have sulfur. And you burn the coal in order to have in a power station, right? You burn the coal in a power station in Taiwan, right? So this causes pollutions because if you burn the sulfur, because the coal contains sulfur, so if you burn the sulfur, sulfur becomes sulfur dioxide in the air. And then if the sulfur dioxide has a contact with water in the air, it becomes H2SO4, which is called sulfur acid. And this is what we call acid rain. So before you release this gas into the atmosphere, you want to introduce this dirty air to this scrubber first before you remove to the atmosphere. Right? So this is what we call scrubber. So SO2 in the absorption or scrubber process, you can, and then you absorb here, and then you can release the rest of the clean air out. Okay? Right. So I have a video for you to let you know what is meaning of the scrubber, because this is industrial process. Right? You want to move this aside. So this is scrubber. I think you all understand now. Another process is distillation. I hope you remember this. We learned this in chapter 4. So distillation, the definition of distillation is the distillation is a process of the separating components, substance, from liquid mixtures to the vaporization and the condensation based on the different volatilities. What is the volatility? So what's the how easy this material can be vaporized, right? So it's the evaporation point of the components in the mixture. So distillation is a unit operation. Unit operation in Chinese is what? 单元操作. That's what you need to learn. Or physical separation process and not a chemical reaction. So this is not a chemical reaction, but this is a very powerful process. Can do the separation due to the different volatility. So distillation is liquid. You remove liquid phase to the gas phase. Okay, so vaporization and condensation. This is the one, and so this is the example. Methanol in an aqueous mixture, you have different vapor pressure. So you do the separation of this. Right, the next one is called liquid extraction. Liquid extraction. What's liquid extraction? Remember liquid extraction, we learned this, and you have this in your final midterm exam. So a process in which a liquid mixture of two species, right? Remember that we call solute and feed carriers is contact with a mixer with a third liquid we call solvent. So solvent will take solute away and leave the feed carrier, right? So that is immiscible or near immiscible with the feed carriers. When the liquid contact solute transfer from the feed carriers to the solvent, the combined mixture is then allowed to settle into two phases that are then separated by a gravity in the decanter. Okay, so we have an example in the chapter 4, which is the mixture of the water, acetone, and MIBK. Remember? So MIBK is what? MIBK is a solvent. Acetone is solute. Water is feed carrier. Remember? Okay, so here is another example. We have paraffinic and aromatic hydrocarbons. This is paraffinic hydrocarbon. This is aromatic hydrocarbon. So how are we going to separate these two? We cannot use distillation, no. So we use liquid extraction by this solvent, which is EG, ethylene glycol. We call EG, ethylene glycol, EG. So ethylene glycol can dissolve this. This is solvent, this is solute. So this one can be taken out from this system to the solvent. And then use this, and then, so this is liquid extraction. Okay? Right. So this is called liquid extraction. So these are all unit operation. The next one is we call adsorption. 吸附. just now we have a absorption, ABSORPTION. This called that was called adsorption, and this one is called adsorption. Adsorption is 吸附. So adsorption is the process which separated do the separation from gas or liquid phase, especially gas phase, to become solid phase. So this is definition of adsorption is a process in which a gas or liquid mixture contact a solid. We call this is called adsorbent. And the mixture components which we call adsorbate, adhered to the surface of the solid. So this is another example. This is the example. You have three types of species. This is paraethylene. This is also ethylene. This is metaethylene. So how are we going to separate this one? You can use adsorption to adsorb this one and remove this two. Okay? So if we have a molecular sieve, this two can be adsorbed. This one can be adsorbed on the adsorbent, and you can get these two free. So that's why you do the separation by adsorption. So we use molecular sieve. That is a pure large enough, the pore large enough to accommodate paraethylene, but not the meta and also osmolar. Okay. So this one will stay in the molecular sieve, and these two will be free to remove. Okay, and another example is called pressure. Another example of the adsorption is called pressure swing adsorption. The pressure swing adsorption is that, remember I just asked you how to separate nitrogen and oxygen. Because oxygen is a small molecular than the nitrogen. So if you have a kind of activated carbon, so oxygen will be trapped in this adsorption, in this activated carbon, and nitrogen will be free. So when you have a column which full of all the activated carbon in this column, so air go in, oxygen will be trapped in this column, and nitrogen will be free to move out. So you got pure nitrogen. That's why you do the mass production, right? And you might have a question, say, oh, well, Professor, if the oxygen was trapped into this column, how can I remove this? So another column is called desorption. This is adsorption, and it's called desorption. So you do the desorption by energy, for example, by the temperature or by the pressure. So oxygen will come out from this way. So you have pure nitrogen and you have pure oxygen. This is what we call pressure swing adsorption. Okay? This is an example. Right. So another example is called crystallization. What's crystallization? Crystallization is a process in which a liquid solution is cooled or solvent is evaporated to obtain a solid crystal of the solute form. So liquid, for example, think of a glass of sugar water. So you remove all the water, sugar will become solid. So this is called crystallization, right? Or a salt water. So you remove water, you become a crystallized salt. Okay? So the crystal in this slurry leaving the crystallizer may subsequently be separated from the liquid in a filter or centrifuge. Centrifuge is 离心, right? 离心机. Okay, crystallizer, remember I show you a crystallizer in chapter 4. Okay, it's a Okay, so these are the crystallizer, and and PSA, pressure swing absorption, and liquid extraction, and distillation, scrubber. These are Lynch machine. These are all the process of the unit operation. So I think you will learn this when you go to the second year. Important to design the process and also how to make it cost effectively. Okay, so we have a few terms you need to know. The first one is called saturated or phase equilibrium. Imagine you have a glass of water and you put the salt into this glass of water, or you can put the sugar into this glass water. So if you put more and more, eventually you will realize there's a limit for you to put the salt into this water. It cannot dissolve eventually. In that case, we call it saturated, right? So when a species transfers from one phase to another, the transfer rate generally decreases with the time until the second phase is saturated. Okay, so this phase 1, phase 2, liquid is the phase 2. Phase 2, the sugar or the salt is saturated in water. That's what we say. So with the species holding as much as it can hold at the prevailing process condition. Okay, that's what we call saturated. And in that case, the phase, gas phase, or this is solid phase and liquid phase, okay, is reach phase equilibrium. So if you think of the water, you have a vapor, this is a closed system, and water vapor goes up, and there's enough vapor water, and the vapor water condense. So this is called phase equilibrium. Okay, this is gas phase, gas liquid phase equilibrium. This is solid and liquid equilibrium. So when the concentration of all species in each phase no longer change with time, the phases are said to be in phase equilibrium. Okay. So here, just want to let you know that the differences between the salt or sugar dissolved in water. You know, salt is a kind of ionic compound. Ionic compound means you have a sodium cation and chloride anion, a chlorine anion. So when you put the salt into the water, the cation and anion will be separated and will be trapped by water. So this is what we call ionic compound. But sugar is not an ionic compound, right? So sugar will be tear away piece by piece, okay, and trapped by water. So these are the different molecular compounds that not dissociate when they dissolve. But sodium chloride, salt will be dissolved, okay, or be dissociated, dissociate. Okay, so now let's move to the section 6.1, single component phase equilibrium. But before we talk about this important topic, let's refresh ourselves first. So the section 6.1a is phase diagrams. I'm sure you know phase diagram very well when you are in high school, right? Am I right? Okay, what is phase diagram? Phase diagram is a phase diagram of the pure substance. It's a plot of one system variables against another that shows the conditions. For example, temperature, pressure, which is the substance exists as a solid, liquid, and a gas. Right? So most common of these diagrams plot pressure on the vertical axis versus temperature on the horizontal axis. So on the horizontal axis is y-axis, right, which represent temperature. The x-axis, which is vertical, vertical axis, which is y-axis, represent pressure, and x-axis represent the temperature. So this is one of the, I'm sure you know this, phase diagram of water, right? So this is solid, liquid, and gas. But if this is water, and what is that? So this is MBP. MBP is normal boiling point. At 1 atm, which is atmospheric pressure, right? And then 0 Celsius, 100 Celsius. This is called normal boiling point. Of course, this is melting point, right? 0 Celsius. So, and this is what we call triple point. Triple point, this is the temperature is 0.01 Celsius and pressure is 0.00603 atm. And at this point, gas, liquid, and solid coexist. And as you remember, this is the critical point of the water, which is 374 Celsius. Pressure is 218 atm. We use TC and PC, remember? So above the critical temperature and above critical pressure, and this is what we call supercritical fluid. Supercritical fluid. What does that mean? The two separating phases never coexist. So this one phase, right? Vapor, and below this is vapor, and above this is gas. And then this supercritical fluid. I hope you remember I showed you a video. So there is no two phases, only one phase. If the temperature and pressure go up higher than this critical temperature and critical pressure, only one phase exists. And if not, you have two phases, right? For example, this line is two phases. This line is two phases. Two phases, right? Okay. You have seen this before, phase transition. So if you want to change from solid to liquid, from liquid to solid, gas to liquid, liquid to solid, or solid to gas, you can do any type of process to transfer, to do the phase transition. So this is vapor liquid equilibrium curve. So you have this curve, the material in this curve has two phases, right? And this is solid vapor equilibrium curve. Or of course, this will be solid liquid equilibrium curve, right? Okay. How about this one? The G, if you have a point here, the G can be represent if you talk about pressure, this is vapor pressure of the substance at temperature T. You can describe this G in this way. Or if you don't want to describe vapor, you want to describe temperature, you can have boiling point of the substance at a pressure P, right? So it depends on how do you want to describe temperature or you want to describe pressure, okay? So again, the same as this one for the F. You want to talk about temperature or you want to talk about pressure. In this case, it's melting point temperature, right? Or freezing point. If it is melting, freezing, okay, on the pressure P. Okay, H is again, you want to describe pressure or you want to describe temperature. Okay? So, just now, this is the case of the water. This is the case of the carbon dioxide. No, this is not the water. Okay. The phase diagram of carbon dioxide. Remember, this is the supercritical point here. The temperature is 31 Celsius. The pressure is 72.9 atm. So if you compare the two types of the phase diagram, you can see that this is water, this is carbon dioxide. So for the solid liquid equilibrium curve, this is solid liquid equilibrium curve here. As you can see, the slope here is positive, the slope here is negative. So if you increase, for the minute this is water, if you increase the temperature, the pressure dropped. But if you increase the temperature, pressure increase. So the freezing point of the water increase with decreasing pressure. which is extremely unusual. So you can, most of the phase diagram for the pure substance represent like this way. If you increase the temperature, you increase the pressure in the solid liquid equilibrium curve. However, water is an extremely unusual case. Because of what? Because of the hydrogen bond, right? Okay, most substances, including carbon dioxide, inhibit the opposite behavior. This is another behavior, which is normal. Okay? Right, so next is that we want to show you an example of the phase transition process. And please use your imagination, because this is called hypothetical experiment. This is 假想的 hypothetical experiment. Use your imagination. This is a container with a piston, and you have a liquid, water, and a vapor. H2O vapor and H2O liquid. So pure water is placed in the leak-proof. So the water won't leak, air doesn't leak. Evacuate cylinder fitted with a movable piston. So there's only water vapor and liquid here. So heat can be added or withdrawn from the cylinder. You can increase the temperature in this system, or you can decrease the temperature in this system. Okay? So temperature can be adjusted to a desired volume. And another condition, another description is absolute pressure of the cylinder contents can be adjusted by varying the force on the piston. So not only you can increase the temperature or decrease the temperature, but you can increase the pressure by press the piston down, or you can decrease the pressure by move the piston up. Okay? Right. So now let's start to know that what's the phase transition process by this hypothetical process. Okay, so this is a phase diagram of the water, as you can see. For the A point to B point is that the temperature is 20 Celsius, and A point moved to the B here. So the pressure increased, but the temperature keep as a constant. So temperature is always 20, but you increase the pressure. So what does that mean? This is the vapor phase, right? So H2O vapor here. So there's no water. In this area, there's no water, liquid water. And you start to push this piston down. And you keep the temperature as a constant, which is 20 Celsius. And then what happened? Pressure increase, right? From 3 millimeter mercury increased to, for example, 17.535 millimeter mercury. Okay, and what happened? When you move from A to B, and then you realize when you go up to B, this is a two-phases system. On this line, there are always two phases. So when you move this one, the pressure will be what? The pressure in this case will be 17.535 millimeter mercury. So the first drop of liquid, you can see a first drop of liquid in this chamber. Okay? And when you keep on pushing this piston, you can see more and more liquid found in this container. But it's still in the B point, because the pressure and temperature will keep as a constant. And you keep on moving, until the last vapor molecule exists in this system. It's still in the B system. It's still in the B point. So point A is a vapor phase, right? And then you keep on moving, condensed at the B point. So it's 20 Celsius, 17.535 millimeter mercury. So this is one phase, which is vapor only. This condition has two phases, which is vapor and liquid. Okay, this is B point. Right. So take place at the boundaries on the phase diagram. This is the boundary of phase diagram, right? There are two phases. The system cannot move off the boundaries until the transition vapor to liquid are completed. So this is in B point, B point, B point. Okay, it stay here. And what happens if you move from B to C? So from B to C is two phases, right? If you keep on pushing, because the last molecular vapor is still here, and then it starts to become one phase. So from two phases become one phase. So constant vapor increase the pressure. Constant temperature increase the pressure from 17.535 millimeter mercury to 760 millimeter mercury. Still liquid, but the pressure increase in this liquid. Okay, so this is C point. It's always increase. The pressure increase until this point C. From 17.5, 20, 100, 200 until 700, 760, right? Up to here. So this is from B to C. How about from C to D? C to D here. C is that you keep the pressure as a constant. You start to increase the temperature. So from this C, right, to D. D is from here. You start to increase the temperature. So the temperature increase, keep it as a constant, and increase the temperature from here, and then you realize if you increase the temperature, and then increase until the first vapor found and go up to D. So this is one phase, this is two phases. This system is one phase, this system is two phases. So D, the first molecular vapor, and a lot and complete, the last drop of water here. Okay? So evaporation at the point D, which is 100 Celsius, 1 atm. So if you understand 100 Celsius, 1 atm, what does that mean, liquid? It's boiling, right? The water is boiling because 100 Celsius, 1 atm. So eventually, all the water, liquid water, will become vapor. So the last drop of the water still here is still in this D point until the last liquid water vaporized. It goes to this point, this point, this point, this point. Okay, take place at the boundaries on the phase diagram. This is the boundary, right, between liquid and vapor, two phases. So this system cannot move off these boundaries until the transition are completed. So transition from what? From liquid to vapor. If it is not complete, it will still stay in the D point until the transition are completed. So from D to E is that you keep the pressure as a constant and you increase the temperature. So the constant pressure increase the temperature, and you increase from here. So temperature increase, right? Temperature increase. Okay? So this is a transition. Use your imagination. This is a called hypostatic process. From A to B, from B to C, from C to D, from D to E. Okay? So if you understand this, we are going to talk about how to do the calculation. So what's the point here? What do you want to know about this? The important thing is that you want to know vapor pressure. Vapor pressure. So you know the temperature, because this is related to the pressure and temperature. You can measure the temperature, but you can calculate the pressure. So how to estimation of the vapor pressure? So here is that how to measure. What does that mean, vapor pressure? Vapor pressure is that if you have more molecules in a gas phase, you have higher pressure, right? So that you can think that, well, if the amount of the molecule increase, the pressure increase. But before we talk about vapor pressure, there's two terms you need to know. Is vaporization and boiling. You know, if you have a pot of water, and then if the temperature is 60 Celsius, let me show you temperature, vapor pressure. So of course you understand, if the temperature is higher, the vapor pressure is higher. So up until you go up to the boiling point. So how do you measure, how do you get the vapor pressure? Of course you can have a Budong gauge to measure the pressure, but can you do the calculation? Yes, you can. Right? So the chapter 6, in the very beginning of chapter 6, we want to know how to measure or how to calculate the vapor pressure. But first of all, let's talk about the volatility. What's the volatility? Volatility is that the volatility of a species is the degree to which the species tends to transfer from liquid state to the vapor state. So that means that how easy the vapor can escape from liquid state to the gas state, vapor state. For example, if you have alcohol and water, the alcohol molecule or the water molecule, you have two types of molecules. Which one is easier to escape from liquid state to vapor state? Which one? Alcohol or water? Alcohol, right? Why? Because alcohol has a higher volatility. Okay? Alcohol has a higher volatility. Of course, the boiling point is lower compared to the water. So we are playing temperature and pressure with the substance. So vapor pressure is that the vapor pressure of a species is a measure of its volatility. So the higher volatility, you have higher vapor pressure, right? So volatility higher, the vapor pressure will be higher. Okay, so we use this symbol. P star is a function of T. So vapor pressure P star is a function of T. If T increase, vapor pressure increase. So we use P star to represent vapor pressure of a pure substance. So how do you estimate the vapor pressure? For example, if a system here, a closed system, you know the pressure, you know the temperature, you know the species or substance in this system. So how are you going to measure how are you going to determine or estimate the vapor pressure? Of course, you can do the experiment. You can check from the table of the water or alcohol or acetone, right? Or you can do the calculation by different equations. This is called, there are some of equations called the Kraepelin equation and Clausius-Kraepelin equation. Right, so this is the Kraepelin equation and Clausius-Kraepelin equation, which we are going to introduce this to you here. So ladies and gentlemen, you don't need to remember this equation, but I want you to know what is this, what is P star represent, what is T, what is this, what are these symbols? So P star, I hope you remember, this is called vapor pressure, right, of a pure substance. Okay, T is what? Temperature, of course, you know that. This is absolute temperature. And delta HV, V is what? Latent heat of the vaporization. What does that mean, latent heat? Latent heat. Latent heat is the energy required to vaporize 1 mole of the liquid. So if you have different type of liquid, you have different latent heat. Okay? This will be defined more precisely in chapter 8. But unfortunately, I don't have time to teach you chapter 8. But what I want you to know is latent heat is kind of energy required to vaporize the substance from liquid to gas. Okay, and V over K, you know that. It's called specific molar volume, right? And if you have sub G, G stands for gas. So specific molar volume of gas. VL, V sub L over K is specific molar volume of liquid. So this is equation you can determine the vapor pressure by these terms: the temperature, volume, and latent heat. So what is latent heat? Just let me give you some examples. What is latent heat? 潜热 latent heat